Hello, today we'll be doing task scheduler. Let's check out this problem. In this particular problem, we are given this particular input called task, and we need to find a way to make sure that we create the fewest amount of instructions needed. And the way to do that for this particular problem is to process each A or B first, and then idle. Idle because we need 2 slots. So let's take this as 0, 1, 2, and then 3. So this is a 1 instruction, and we need to wait until 3 before we can make this instruction again. And for B, because we did it at 1, this particular item, we did this at instruction time 1, we need to wait until 4 to do this, make this instruction. I think we start with 1 instruction at the beginning. Okay, because 0 is here. There are no instructions. Nothing has happened yet. So this will be, let's say 4, and so on and so forth. Before we can insert this, we can re-add these back into some sort of like a data structure where we can process these again. So first things, we need a queue. And a way to keep these things in order is to use a max heap. Well, of course, we're using a min heap because when you have min heaps in Python. So we just throw in the -3 because we have 3 of these. And we don't actually need to care about the values at all because, well, it's not necessary. We just need to make sure that we process these properly. We just need to process these by account. So with that, we keep a counter of CPU time, and we start at 0, and we start processing things. Of course, we don't start with everything in the queue. We start with nothing in the queue. And what we need in the queue is actually the current time needed, how many counts there are, and when we can start processing them again. So let's start with a min heap. Let's say we have this min heap data structure and we have these counts. And so we process this and we move it out of the min heap. And of course we throw it back into the queue of 2. And let's say, see it was processing time 1. Now let's say processing time 1 plus 2 is equal to, well, isn't 1 plus 2 equals 3? Yeah, it is. So at that particular time, we can insert this back into the min heap to be reprocessed. Anyways, so now there's still stuff in the min heap, but we're still not at 3 yet. So we're gonna take that out of the min heap, and now we have -2 and 4. As CPU time shifts to 2, and now we hit 3. Once we hit 3, we can now take this item, take this -2, and pop it back out of our queue, and throw it into our min heap. And now we can advance our CPU time because there's nothing else left to do. Once we hit 4, we also process this min heap item, right? And throw that into our queue. We have a -1 and a 4, 6, and we're done with this item. And if we still have something in the queue, we can throw that into the min heap right now. So we have -2, and throw this out of the queue. Now CPU time 5, we can process the 2, as you can see the B here, and once we process that, we have -1 and 5, 7. So now we can process 6. 6, we throw that in back into the heap. So we have -1 here, and then CPU times 7. Of course, we process this -1 first. This becomes 0. Of course, we don't add that into our queue anymore because it's 0. We don't have any more items. And once it hits 7, we put this -1 back in, and then we move to 8, and we complete this process and finish off -1. And now we have a total of 8 items once the min heap and the queue is empty. And with that, we can complete this particular problem. All right, so let's get it. So let's create a CPU time. Starts at 0. Let's create a counter to make sure we have all the counts of the task. And let's create that min heap that we're talking about. So that's going to start with a negative count, 4 counts in counter dot values. With that, we're done with the min heap. Let's take a look at that queue. So the queue is going to be DQ. Makes it easier to pop things and not pop things. So with that, are we missing anything? I don't think so. Let's just get it. So wait, we need to heapify the min heap though. All right, done there. Done deal. With that, we can do while min heap or queue. And every time we do a CPU time plus equals 1. With that, we check the min heap first, and then we check the queue. So if min heap, there is something in the min heap, so let's pop it out. So our count is equal to, let's say, 1 plus the heap queue dot heap pop of the min heap. So we add 1 to the current time. So it's a count of the items in the min heap. So if count, that means it's not 0 yet, then we can add it to the queue. We're gonna add the count, and we're gonna add the CPU time plus the instructions, cost per instructions, which is n. So I think that would be clear here. And with that, we can now process our queue. If queue and if reuse count and reuse time is equal to queue of at 0, and if reuse time is equal to CPU time, then let's push it back into our min heap. And let's pop left. With that, we are done with this particular problem, and let's return the CPU time. Okay, right. Usually, let's see. Oh, queue again. All right, looks good. And let's submit it. All right, great. And that's how we do this particular problem. So again, what we did was that we kind of ignored the variables. That wasn't a necessary piece of information. We could keep it inside our queue and heap if we wanted to produce this particular permutation and build up this particular string about the instructions that we needed. But we didn't need to do that, so we kept it out of our data structures, and that way we made it a little bit simpler. This was very inherent about a CPU time and when we can process things using a min heap and what we should process and when we can add it back into the heap. And with that, we have completed this problem. If you enjoyed this video, like and subscribe. Want more videos, check the link in the description below. Thank you very much, and I'll see you in the next one.